Today I am going to discuss about strongly connected components. It is the one of the application of DFS, depth first search. So decomposing a direct graph into is strongly connected component is one of the application of DFS search. What is a directed graph? A directed graph it has a direction. If there are two vertex u and v, then it will be specified as a direction from u to v. So a directed graph is strongly connected if there is a path between all pairs of vertices. Suppose if there are three vertices are there, u, v, x, then if there is a path from u to v, then there is another path from v to u. So here, and if there is a path from v to x, then there is a path from x to v. So every vertex in that graph has there is a path in between each other. So a strongly connected component SC of a directed graph is a maximal strongly connected subgraph. So suppose a directed graph G is equal to VE. V is the number of vertices in that graph, E is the edge set in that graph. A strongly connected component of that graph is a maximal set of vertices. C is a subset of V such that for all uv in this v is the vertices of that graph, we are select some subset of that vertices c, and which has two vertices, suppose u and v. Such all vertices in this c, both there is a path from u to v and also u to v and v to u. That means both u and v are reachable from each other. In other words, we can say that two vertices of a directed graph are in the same component if and only if they are reachable from each other. If suppose u and v, if there is a path from u to v and v to u, then we can say that these u and v are in the same component. Then next, another example of a graph which consists of four components. One is C1, another one is C2, C3 and C4. So C1 is here and C2 is this, C3 is here and C4 is this one. So four strongly connected graph is here, and here if consider this vertex as u and this vertex as v, then if it is a strongly connected component, that means there is a path from u to v, then also there is a path from v to u. And if there is a path from this component, if it is an x, then there is a path from x to v, but there is no path from v to x. So it is not a single component. These two are in different component. That is explained here. If a graph an edge from some vertex in Ci to some vertex in Cj, this is a Ci. Suppose this is Ci and this suppose this one is Ci and this is Cj. Then I and j are not equal because this is C1 and this is C2. So these are not equal. Then one can reach any vertex in Cj from any vertex in Ci but not return. Here we can reach from C1 to C2. Here also we can reach from C1 to C2. But we can't reach from C2 to C1. There is no path from C2 to C1. So these are two different components. Then algorithm. Here this is the algorithm of a strongly connected component. We are passing the graph G, and first we call the function DFS of that graph and compute the finishing time f of u for all vertices u, and then next step is computing the transpose of that graph. We are first we are pass DFS algorithm of the graph, and then we compute the graph transpose, then again perform the DFS algorithm on this transpose of that graph, and output the fourth step is output the vertices of each tree of the depth first forest formed in the second DFS as a separate SC. So we will take the output of the vertices of this second DFS traversal. Then here time complexity, here we use a DFS algorithm. So DFS algorithm time complexity is order of V plus E. So the time complexity of a strongly connected component is also order of V plus E. Then this is an example of a graph G is equal to VE. First we call a vertices called DFS of G. Here we are starting from C. Initially start from C. C is 1 bar. Then there are two paths here, and we can go to here. I select G. So here second one is 2. Then from the G we can go either H or F. We can go here and F. So I select this path F. So its value will be, discovering time will be 3. Then from the F we can only go to G. There is only one outgoing path is here. So G is outgoing to G. But G is already visited. So here finishing time is 4. Then come back to G. When G is an outgoing path H. So it is not visited yet. So we will move on to this path H. Now the discovering time is 5 here. Then there is no only loop is here. So here there is no outgoing path there. So its finishing time will be 6. Then return back to here. G, all its child nodes are exploded. So its waiting finishing time is 7. Then come back to here. C, to C. C, there is an unknown visited, that is D. So its now its finishing time is 8. Discovering time is 8. Finishing time is 9. Then next, all its node near of this node is exploded, neighbor of this node is exploded. So we will come back to this node. Then finishing time is 10. So this portion is exploded. Then next, here remainings are there A, B, E. So we will start from any node. Here we start from B, is 11. Then move to here. This node is already explored, so we can't explore this node. Just come here, it is 12. Then is here node which is not exploded here, so its value is 13. So all its neighbors are exploded, so finishing time is 14. So come back to here, its finishing time is 15. Then come back to here, its finishing time is 16. So all nodes are exploded here now. Then next we need to find out the G transpose. How to find out the G transpose? Here all the arrow is represented in the reverse order. So here this arrow will be opposite and this upgoing arrow will be downwards, like that. All arrows will be changed its direction. Then next step is perform the DFS on this DFS on this algorithm. Then here we can start from any node. We can select from here. We are start from the order from which has the maximum decreasing order of the finishing time. So which node will be first search? First search the maximum finishing time, that is 16. So we will start from this node. This is considered as 1, then 1 bar, then outgoing node of this only this path. So next to this one is 2, then next bar is outgoing is here 3. In this we are starting from F which has the maximum finishing time, that is 16. So from this here we are started as 1, then next you move on to A is the 2, and next here it is 3, then node to explore here we already explored here, so finishing time is 4. Then move to backward. Here all nodes are its A's or neighbors are explored, so finishing time is 5. Then comes back to here, all nodes are its neighbors are adjacent nodes are explored, so here 6. Then next largest finishing time, here it is 10. So we will start from C. So C has one outgoing here, B, adjacent is B, it's already explored, so we no need to explore this node. So another node is here. So here it is, maximum is 6, so here 7. Then next here it is 8. Then all its nodes are only one adjacent, that is C, so all its neighbor nodes are explored. So here D is finishing time is 9, here it is 10. Then next largest finishing time is here 7, G. So start from G, 11, and here node to explore here it is 12, and all its neighbors are explored, so 13 here, then it is 14. Then last one is H, that is 15 bar 16. So this is the finishing compute the or pass the DFS on the GT. Then we will get a, here it is 16. This one is single component, H is a single component. Then when we consider this is a consider as a single component, and here we consider this is as a 10, 9. According to the finishing time, this is a component, and here from 6, 5, 4, this is another tree. So there are 4 components are there, that is shown here. So here call the DFS of GT, that is a transpose of that graph, but this time consider the vertex in the order of decreasing finishing time. So we will get ABE as a one component, CD as another component, H as a single component, and FG as another component. Then output the vertices of each tree in the DFS as separately strongly connected component, that is ABE is a one component, another component is FG, and H is another component, and next component is CD.